Seminar speaker is Jelani Williams. Jelani currently is the first-year President's postdoc fellow in our department. His research, including applied probability and decision making under uncertainty. The goal is to guide the development of robots and to do the performance analysis and covers like multi-server system and reinforcement learning system and so on. Okay. Jelani graduated from CMU, he's advisor to Green Wang and Williams work with them. Yeah, okay. So Jelani, get started.
Yeah, so hi everyone. Today I'm going to talk about setup times in multi-server systems, as well as some sort of new results we've gotten in that space. And all of this is joint work with my wonderful collaborators, Wayne Wang and Moore Harklebalter. Okay, so let's get started just with an overview. I'm going to split the talk into 4 parts, as usual, if you've seen any of my other talks. And the first part is just going to be a basic introduction to setup times. And the second part, we'll dive a little bit deeper into the problem setting that we're considering. The third part, we'll talk about our results and sort of the key technical challenges and ideas that allowed us to overcome those challenges. And in part 4, I'll sort of very briefly describe some future work as well as sort of the things that I'm interested in these days. Okay. So the first question that I want to answer is, what is a multi-server system? Because I imagine most of you aren't queuing theorists. And so what we do in queuing theory is we study places where waiting happens. So for example, if you go to a supermarket or something, and you go to check out, you end up waiting in line to check out. If you submit some kind of machine learning job, like an image generation job, you end up waiting for that job to be served. Or if you go to the bank, you're waiting to see a teller, you're waiting. And so what queuing theory does is we make an abstract model of those systems where waiting is happening. And by analyzing this abstract model, we can get results that sort of describe the behavior of waiting in all of these different systems, right? And so what I have drawn for you here on the slide is just sort of the abstract representation of a queue that you may have seen in other settings and maybe not have understood. Okay. So a multi-server system is just an example. It's just a queuing system where there are multiple servers. And so, for example, if you go to a supermarket and you go to check out, oftentimes there's not just one cashier working at the checkout. There are multiple cashiers, and you're free to use any one of them. They're essentially interchangeable. Okay, so that's a multi-server system. What then is the setup time? Okay, so for many servers, you can turn servers off and on. For example, if you have a cashier, you can say, okay, business is pretty slow, you can go home for the day, right? And in almost all of these settings, you can turn a server off very quickly, but to turn it on takes time, takes a significant amount of time. So if you remember using a photocopier back in the day, right, if you're the first person to use that photocopier, it's going to take a really long time for it to set up. But once it's ready, like basically anyone can use it very quickly, right? You can also think of maybe preheating an oven, or you can think of spinning up instances for an application that's hosted in the cloud, right? In all of these cases, you're dealing with setup time. Okay, and so why do these setup times actually matter? Why do we care about setup times? The reason for that is that setup times can actually hurt queuing. Right? So for example, if setup times are long compared to the typical size of a job, and we're turning servers off and on regularly, then there's a chance that setup times are significantly impacting the queuing delays in our system, right? And so when I say long, I really do mean long in this case for setup times. So for example, if booting up a new instance of your application takes around 10 seconds, which is very, very fast, and your average job size or the latency that you're trying to target is around 10 milliseconds, then that's 1,000-fold difference in size right there. And like the 100-fold or 1,000-fold, 10,000-fold, it's very common in a lot of computing applications, this difference between setup times and job sizes. Okay, so one thing also is that unless we're dealing with new technology, it's sort of hard to control for this, right? You can build out a new system that maybe has different setup times. You can sort of maybe experiment with strategies like sort of varied sleep states, but in a lot of cases, this is something that's kind of out of our hands. Right? And so on the other hand, let's look at, why are we even turning off our servers, turning on and off our servers regularly, right? Why don't we just use all of our servers all the time? And the answer to this question is an answer that you've probably heard a lot. The answer is money, basically, right? If you're providing service in a multi-server system, then you don't want to run all of your servers all the time, because the more servers that you're running at any given moment in time, the more operating costs that you'll have to pay, the more energy that you end up burning, right? On the other hand, from the user point of view, they want you to be using as many servers as you have at your disposal, right? Because they want to wait as little time as possible. People hate waiting, right? And so the delicate balance you're trying to strike by turning servers off and on is, being able to satisfy this quality of service for your users while using as little energy or as little resources as possible on the provider side. Okay, so that's the basic setup of the problem. And from here, it would make sense that we'd be interested in how to do this dynamic provisioning in an optimal way. So we can optimally trade off between the costs that the provider pays and the amount of time that the user spends waiting. Unfortunately, this talk is not going to be about that. It's going to be about far more basic questions, like for even very simple policies, how do setup times end up affecting the waiting time, right? And the reason that we're trying to answer this question first is that in order to do any kind of optimization, usually you need to understand how performance behaves just on like a basic level, right? And that's something that we don't understand at a very high level these days. Another question that we're going to be interested in is when we're modeling the effective setup times, what aspects of setup time can actually be ignored, right? It's very typical to make all kinds of assumptions when you make a model, but if we lose something by ignoring certain aspects of setup time, then our model is going to be less useful than it could be, right? And so the sort of spoiler for our answers to these basic questions is that setup times can cause profound increases in waiting time. And this is especially true if your setup times have low variance. And this is actually very surprising to all of us working on this project. And it's been fairly surprising to the audiences where we presented this work, because usually you're not saved by variance. Usually variance ends up hurting you in a queuing system. And so we'll talk a little bit about this very strange result as we move forward. Okay, so that's a basic setup, and that's the end of part one. And so now let's talk about in more detail the model that we're going to be considering and sort of prior work, what's hard and what's no. Okay, and the best way to do this, I think, is to let's widen a bit. So our model is the MMK setup. And if you've taken queuing theory, then maybe you've heard of the MMK. Hopefully you've just by osmosis have at least heard of the MM1. And I'm going to go through the basics of that model. Right. So this is our queuing system. There's a central queue, as well as K equals 4 servers. Right. That's what the K stands for in MMK. Okay. And jobs are going to be arriving in a Poisson process at rate K lambda. And that Poisson process, that's one of the M's in our MMK. It's the first M, and that means that arrivals are going to happen in a memoryless way. If you look at sort of a small delta step of time, sort of it's independent whether an arrival happens in that time. Okay. Okay. Jobs arrive into this central queue. They wait until they get to the head of this queue. And at some point, they're going to be served at one of these servers. And a job remains in service at one of these servers for exponential mu time, at which point ends up leaving the system. Okay, so those are the basics of the MMK. And the system we're going to analyze is essentially a variation on the MMK. So all that's left to do is to describe how the setup process happens, how we're going to be turning off and turning on servers. And the best way I know how to do this is to just go through an extended example and sort of describe how we end up turning servers off and on. Okay, and so to start this example, all of our servers are going to be busy working on jobs. That's what those blue rectangles are. Okay. Okay, and so say one of the jobs finishes service and it leaves. Then what we're going to do is turn that server off immediately. Right? There's no work for it to do, so we just turn it off. Okay. Likewise, if another job is to leave, then again, we have a server idling, and so we turn it off. Now, if another job arrives, it gets to the head of the queue, and it notices that there are two servers just sitting off, and so it starts setting one of them up. Okay. And we're going to use this green hourglass to denote a server that's currently setting up. Right. And this sort of arrow that I've drawn is just sort of, that's the job that's going to call dibs on that server. Okay. And the setup time, the amount of time it takes before this server is actually ready to serve a job, we're going to denote with this the symbol beta. Okay. And in this case, sort of usually throughout this talk, beta is going to just be some deterministic number. But in cases where the setup time is a random variable, beta is going to be the average setup time. Okay, so to continue our example, we're going to say another job arrives. Okay, it again is going to see a server that's off and start setting up that server. Okay, but if another job arrives, obviously there are no more servers to start setting up, and so it doesn't do anything. It just waits in the queue. Okay. Now, if more time passes and a job leaves, then the job at the head of the queue moves into service, and all of the jobs move forward in. Okay, and so again, if this happens, the job at the head of the queue goes into service. We move into the head of the line, except now the server that the job, now it's the head of the queue, that server, this sort of bottom server has no job associated with it. And so even if it were to finish setting up, there would be no work for it to do. And so we just preemptively cancel that setup process. Okay. Right. And of course, if the server finishes setting up, then the job enters service at that server. Okay. So this is the basic policy that we're going to be analyzing.
Jelani, a quick question. So this, the cancellation works out because you have poson arrivals, right? Suppose it, but in case it was a different arrival process, then based on the hazard rate, you may want to cancel or not cancel since the last time an arrival came in. If you expect an arrival to happen more very soon, then you would probably keep it going.
Right. That's a good point. That sort of certainly this is true in the one server case, right? Well, in the one server case, like if you have a job waiting, you always want to be setting up your server. But sort of, you've made a great point that depending on sort of the arrival process, you might anticipate more jobs arriving sooner. But there's also another point that you could have made, and that's that sort of depending on the load of the system, if the number of servers currently running is small, you might not want to cancel that setup anyway, right?
Yes, yeah. Mm-hmm.
Right. And so these are both good points. And so, yeah, I guess this policy is not necessarily like the best policy on earth, but hopefully it's one that we can analyze. Actually, we end up being able to analyze it quite well. And so it's a good point. Actually, there's one variation on this policy that I want to introduce now as well. That's somewhat solves this, that somewhat addresses the problem that you're talking about. Okay. And we're going to do that by introducing a parameter m. Okay. And that m quantity is going to be the number of servers that are allowed to idle before we shut off a server. So, for example, in this case, if this job departs, then this server that's sitting idle at the bottom is going to stay on, right? But if another job departs, then now there are two servers sitting idle, and so we end up turning off one. And you can think is sort of you scale this m quantity that you'll be less hasty about turning off servers, right? And so maybe this can sort of mitigate the problems that you end up seeing in systems with setup times. Does it kind of address your question, Vijay?
Yes, yeah. No, that makes sense. Setting some aside if possible, that would be good. I mean, some stickiness is always a good thing.
Right, of course. Okay. And so that's the policy.
Beta for each server is the same.
Right. So the question is, are we assuming the beta for each server is the same? And we are assuming it's the same. We're assuming all the servers are identical in their sort of system properties.
So I was thinking, like, if they're not the same, but you have two idle ones, then maybe you need to choose.
Right. This is a good point. Yeah, if they're not the same, if you have two idle ones, you need to choose. And actually, the choice that you're making is kind of non-trivial, right? It's not clear whether you should be keeping on a server that starts up quickly or keeping on a server that starts up very slowly. Depending on like whether you plan to be sort of turning off and on the server sort of very regularly. So yeah, it's a good point.
The question is that if currently a new job comes and it will go to this empty server, and will that the last server going to be starting to set up, or wait until another job in the queuing system it will set up?
We're going to wait until, that's a great question. And if two jobs arrive to the system, or if one job arrives to the system, it enters service, and the server that's currently off, we don't start setting it up. Right. This is a very important point to be made. But actually, even if we did, I've sort of run simulations, and I've thought about this from a theoretical standpoint. Even if we did start setting it up, sort of the results that I'm going to show you, they're not going to change very much. Okay, so that's how setup works. Are there any more questions? Very important. Maybe it's the most important part of the talk, just sort of to understand the model. Okay. All right. So before we move any further, what I want to do is go through some notation for the system. And these are just basic state variables that will end up coming up later on in the talk. Okay. The first state variable I want to mention is the number of jobs in queue. We're just going to use Q of T to denote that. Okay. We're going to use Z of T to denote the number of busy servers. And we're going to use N of T to denote the total number of jobs in the system. So that's the number of jobs in queue plus the number of jobs that are currently in service. So now I'm going to briefly sort of point out that if we're running an M policy, this isn't like a complete state description at all. Right? Actually, even without an M policy, it's not a complete state description, because we need, in order to have a complete state description, we need to keep track of all the remaining setup times of the servers, right? Which is potentially like very complicated. And also the number of busy servers is distinct from the number of servers that are on. It's another important point that ends up coming up. Okay. So now that we've described this problem, I want to ask the question, what makes setup hard to analyze? And I'm going to give you two reasons. And the first is that the effective setup can be indirect. And this is true even in the single server system. And I've drawn sort of like a short cartoon that sort of illustrates why that is. Okay, so imagine we're starting from an empty system. At some point, a job arrives, and the one server in the system starts setting up. While that server is setting up, more jobs are arriving behind that initial job, until at some point, the job at the front enters service. Now, all of the jobs that were around while the server was setting up, right? They know exactly why the line is as long as it is. They know where their increased waiting is coming from, right? So they've been directly delayed by the server setting up. On the other hand, all of the jobs that arrive after this point are going to be indirectly delayed by setup time, right? They're delayed by virtue of the fact that the line is really long. And I'm certain this has happened in practice in many different cases. Like if you go to an amusement park, for example, at like maybe an hour after opening, you might be wondering, why is the line so long at this point? It's because the line has been long for an entire hour. It's because of this sort of buildup of a queue that happens before you get there. Okay. And so this indirect delay is something that you have to work at, that you have to deal with when you're trying to theoretically analyze these systems. Okay. And there's a second point, which is that in the multi-server setting, there's sort of the state space is complex, and the state space interactions are sort of complex as well. So in particular, you need to track your remaining setup times, as I was talking about before, but also the sort of the setup behavior of each of your servers is determined by, you know, how quickly your other servers are operating, how quickly they can get rid of jobs. Okay, so if there are many departures from the part of our system that's working, then we might end up canceling the server that's in setup. But if there are very few departures, right, fewer departures than we need in order to sort of stabilize the jobs, in order to deal with the sort of continuous flow of jobs into the system, then we might end up setting up this sort of server that we have off right now, right? And so there's some kind of complicated interplay between the state variables in the system. Okay. So that's at a high level, just two things that make setup hard to analyze. Okay. So now let's address what's known about this problem. And we'll start with the single server setting. In the MG1 setup, which is sort of very general conditions. So in particular, it's memoryless arrivals, but general service times and general setup times. Peter Welch in 1964 showed how to get the full distribution of waiting time, right? And sort of things have developed to a point that this is something that you'll learn how to do in your sort of graduate queuing class in like a class or a couple of classes. The sort of natural extension to this work in the multi-server case, which is the MMK setup, the thing that I've spent time describing, everything is basically quiet for 50 years. Now, this isn't exactly right, because people were working on models like staggered setup models where only one server is allowed to set up at a time. And they were also working on sort of multi-server sort of vacation models where at certain points in time, like a server can kind of disappear for a while and then come back. But for this particular problem, where setups are being driven by arrivals and departures, things were pretty quiet for half a century. That is until the work of Anshul Gandhi in roughly 2010. He had this sort of beautiful theoretical paper in 2010 that sort of spawned a line of work for a decent amount of time afterwards, in which, you know, this work can sort of maybe be considered a spiritual successor of. There's one thing that sort of it's very striking about this line of work, though, and that's that in this work, they assume that setup times are distributed exponentially, and this turns out to cause some problem from a modeling point of view. Okay, and so let me describe exactly what I mean by problems. The first problem is that exponential setup times in this setting are like pretty unrealistic. And I mean that in a couple of different ways. One is just that, you know, if you look in practice about how setup times are in the wild, setup times are closer to deterministic values. There's maybe like a little bit of noise around the deterministic value, but it's pretty close to deterministic. And this is something that's explicitly noted by the authors, and so much so that when the same authors go on to do sort of like practical simulation work, they will assume that setup times are deterministic. Okay. The other thing that's unrealistic about exponential setup times is that this variance kind of leads to odd behavior. The more servers that you have in setup, right, the more quickly the next server ends up finishing setup. The next server kind of arrives, and so this is just a property of the memoryless property of exponentials, right? If you have 100 exponentials and you're waiting for the minimum of 100 exponentials, that ends up happening sort of 100 times faster than if you were just looking at it, right? The last thing, right?
Means what?
So this means that, for example, if you started setting up like 100 servers simultaneously, just like at time zero, you started 100 servers setting up, and you asked, okay, when is the first server going to finish setting up, right? In expectation, that's going to be 100 times smaller than if you just had one server that was setting. Okay, and this is a property of, this is a property of exponential,
Which is unrealistic in practice.
which is unrealistic in practice. In certain cases, there are certain cases, of course, where maybe you do get sort of a benefit of variance, where like sort of by requesting 100 different. It's hard to come up with an example that is actually reasonable, but you can imagine sort of processes where there is some benefit of variance, right? Maybe you like request 100 Ubers, and like maybe by chance you end up being assigned to one that's like much closer to you.
That's inevitable if you have random set of times, right?
Well, you have to be careful about inevitable, right? It depends on specifically like how the randomness like exists in the wild. So for example, if you're setting up a virtual machine, right, this is arguably a kind of sort of random process, but the randomness is such that there's sort of a fixed deterministic amount of time that something like this is going to take, and then there's sort of random noise tacked on at the end and sort of interspersed within it. Right. And so like maybe if
The exponential
Right.
shift.
say again,
Exponential with the shift.
exponential with the show, like deterministic plus exponential or something. Yeah, it's good model things. Though oftentimes, like if we're talking about like in a computing context, it might be something more complicated because like maybe setup times end up being correlated with each other. Like if it's because of like network IO or something, right? Then like if the network is congested, then it's congested for everybody, and maybe you end up with correlated setup times, and yeah, but yeah, it's yeah. At the very least, I'll say that maybe just exponential is not the best assumption, and maybe the first step that we're going to take is by assuming that things are deterministic. Okay. So this is the first problem, and of course, actually, upon consideration, these problems aren't actually that big of a deal. Just because the sample path behavior is a little bit odd, and just because in reality setup times are closer to deterministic, that doesn't mean that the exponential model isn't a useful model, right? What matters in terms of usefulness is whether it's actually predictive of what happens in the real world, right? If it makes no difference whether things are exponential or deterministic, fine, assume they're exponential. It doesn't matter. The problem is it does matter. It ends up mattering a lot. Assuming that setup times are exponential will lead to poor predictions of performance. And I think the best way to illustrate this is by showing a plot, showing some simulation results. Okay, and so throughout this plot, we're going to assume that the setup time is a sort of the mean setup time is 1,000 milliseconds or 1 second. The load is 50% or 0.5. And you can think of this as just sort of the average fraction of servers that are busy. Okay. And the mean service time, the average amount of time a job takes, is going to be 1 millisecond. So we're going to get this 1,000-fold difference that we were talking about before. Okay. Right. And what I'm going to plot is on the y-axis, it's going to be the expected waiting time of a job in this system in milliseconds. And on the x-axis, K, the total number of servers in the system. Right. So we're scaling the system at constant load and seeing how the average waiting time ends up behaving. Excuse me.
How is load related to the arrival time?
Load in this description is independent of the arrival rate because if you'll recall, in the model section, I said that the jobs are arriving at rate K lambda,
Oh,
right? So it's sort of, and this is not a necessary assumption to make in terms of like the results we get, but it's just sort of a nice way to illustrate what's happening in these systems. Okay. All right, so the first thing that I want to show you is the no setup line. It's this green line, okay? And the MK with no setup, it starts with pretty short waiting time, just 1 millisecond, and it decays exponentially. And just as a point, this is a log plot, right? So straight line, so polynomial decay is going to look like a straight line, whereas exponential decay or super polynomial decay is going to look like this curved line that you see in the gray case, or in the green case, in the no setup case. Okay.
sorry, what's lambda here? Where's lambda?
So lambda is part of the definition of rho.
Oh, it's part of.
Yeah. So rho is lambda divided by mu. Okay. Right. And so no setup case, it decays very quickly. The exponential setup case decays like fairly slowly. I mean, the setup time is quite large. But the deterministic case decays extremely slowly, much more slowly than the exponential case, to the point where if you have like 100 servers, right, these waiting times differ by orders of magnitude, right? It's 100 milliseconds in the deterministic case, whereas it's under 10 milliseconds in the exponential case, right? And so from a provisioning standpoint, this is a big deal. You will end up with very like incorrect predictions if you use an exponential model instead of a deterministic model, right? There's a huge gap between these things. Okay. Right, and this is just to kind of illustrate in a provisioning example like how far your predictions will end up being, right? So if you were trying to get a target waiting time, say of 20 milliseconds, right? The exponential system would predict that, okay, after you scale the system to like 50 servers, then you're going to be under 20 milliseconds. Whereas if you look at the deterministic system, which is, you know, as we've argued, closer to reality, then you're going to need to scale the system to 2,000 servers, which may not even be feasible. You know, it might not be a reasonable thing to even consider. Okay. Okay, so this is kind of a big problem. And so given that this is such a big problem, it's worth asking why people assume that setup times are exponential in the first place. And the reason for this is precisely that memoryless property of exponentials, right? If you're looking at if you're looking at a description of the system, you no longer need to keep track of the remaining setup times of each server. You can now just keep track of the number of servers that are setting up at any given moment in time, right? And this is, I mean, you can clearly see this is a much simpler state space, and it's much easier to use sort of existing methods of Markov chain analysis to analyze these systems.
Yeah, waiting time, is it in steady state or
The expected, yeah, that's in steady state, or as close to steady state as my simulations provide me. Yeah, this is a good question because it's sort of there are various metrics you could look at for waiting time. But yeah, this is steady state. Okay. So that's kind of a short description of our model, what's hard and what's known about it. And now let's sort of get into what specifically we were able to show. And the first thing that I want to do is just give you a visual representation of our results when this im parameter is equal to 0. Okay, and that's, if you'll recall, that's the initial extended example that we were talking. Okay, and in this case, we have an upper bound on the expected waiting time in steady state, a lower bound on the expected waiting time, and you have a sort of startlingly accurate approximation to the waiting time, which applies like very, very generally. Okay, and so we've essentially been able to almost perfectly characterize the waiting time of this system. In particular, we show the following theorem sort of informally. For R large enough, where R is k times rho, or the average number of servers that are busy in the system. And for setup time large enough, this beta quantity, then the expected time in queue of a job is going to be like up to a multiplicative factor equal to the setup time divided by the square root of R plus 1 over mu times k times 1 minus rho. And this is a very simple result. If you actually look in the paper, you know, the result that we proved, the theorem that we proved, doesn't look exactly like this. But this captures everything that's going on. This captures everything that's going on with the average waiting time in a tight way. Okay, and sort of if we break down these parts, we can see that that sort of the setup time part scales with linearly with the setup time, and with the inverse square of R, with the number of servers that we have active. But there's also sort of a separately scaling resource contingent component, which has nothing to do with the setup time at all, which is somewhat strange, but it's actually reminiscent of some of the earlier work that you see in the MG1 setup, for example. You get the same kind of decomposition of the effective setup and resource contingent there. Okay.
Yeah. Just a quick comment, that decomposition is very similar to what used to happen. I mean, your setup time is like a server vacation. And I think in the vacation model, you have the exact decomposition of there's a vacation component and there's a resource component. Yeah.
Yeah, thank you for that, BJ.
State location, which variables?
Right. And so this is why in previous versions of this talk, I've sort of omitted using theta, but you can think of this as just being tight within some multiplicative constant. Okay, so there's like an upper bound, which is some like C sub H times this, and there's a lower bound, which is some C times that, C sub L times this. And that's what this means. Yeah. So for the theorems that we show, we assume that both beta and R are larger, beta and mu times beta and R are larger than 100. This isn't necessary to prove the results. It just makes the results like somewhat nicer to derive. Okay, and you'll see later that when we look at the approximation, that actually it doesn't seem to need these assumptions at all. Okay, and so sort of complicated part of our approximation is this following formula. Don't worry about reading all the different parts of it. I just wanted to sort of to put it on the page just to see that it's not a super crazy formula. It's more interesting, I think, actually, to look at how well this approximation ends up working. And so this is what I'm showing you is, again, well, slightly different from before. On the y-axis, we have the average waiting time, again in a log scale. But on the x-axis, we're varying load from 0 to 1. Okay. And so each row is going to be some number of servers. So in the top row, k is equal to 10. In the second row, k is equal to 100. In the third row, k is equal to 1,000. And in the in each column, we have a different setup time value. And you'll see that, like, no matter how you scale the system, by increasing the number of servers k or increasing the setup time beta, you end up with like a very good approximation of what's going on. This is with the specific caveat that your R value isn't too low. When your R value, when the expected number of servers you're using is smaller than 1, then you end up shifting into a type of behavior that's actually closer to what happens in the single server case, right? And this kind of makes sense because you only actually end up using like one server most of the time in that case. Okay.
And is there no result for the single server case when you have this setup time?
So there are known results. So they've characterized the complete like waiting time distribution. Yeah, that was right.
Yeah, sorry.
Right, and this to be clear, this isn't exactly that formula, right? Because if that were the case, like when R is equal to 1, then you'd get like some kind of vertical asymptote. But it's what I'm plotting here is actually the additional waiting time that you end up incurring due to setup in the single server case. And it seems to match the shape very well. So we haven't like explicitly looked at that from a theoretical standpoint. Right. So that's the approximation result. And so I just want to stop here and talk about like what's cool about this. This is really kind of the first explicit average waiting time result for a finite server system in this MMK setup kind of model, right? And that's not for lack of trying. Like a lot of that sort of big list of papers that I showed you before were all kind of trying to approach this from different angles. Okay, but usually the results they got were looking at like sort of some kind of infinite scaling of the number of servers, whereas this is these are explicit bounds that sort of happen regardless of any kind of scaling. Okay. And this is also the first analysis at all of a system with a deterministic setup time, particularly the multi-server setup system with deterministic setup times. Previously, everything had kind of relied on this exponential setup assumption. Okay, so I thought this was interesting, and I'm going to note here that actually, as part of this work, we didn't just consider like the m equals 0 case. We also proved a lower bound on the general m case, and we showed that if your m is too small, then actually you don't get much benefit in terms of the effect on your average waiting time. And that's illustrated by the figure that I'm showing you right now. Again, we have the average waiting time in the y-axis and the total number of servers on the x-axis. And this sort of bunch of lines you see at the top are the MMK setup sort of without any M, and the MMK setup with sort of a somewhat slowly growing M. And M is scaling as R to the 0.3. Okay. And even when you increase the scaling to r to the 0.5 or square root r, you don't get like a huge difference in the average waiting time of your system. And even when you bump things up to r to 0.6, it's still like, it's pretty close. It's only once you sort of increase it significantly that you end up getting some kind of some sort of significant phase transition in the behavior, like with r to the 3/4. Okay. Mhm.
So MP is the number of idle servers you can keep.
Right.
So do you actually observe some like phase transition when you increase the exponent? Like suddenly it's go from minimum benefit to significant benefit.
So we don't really observe a phase transition is probably the wrong word. What we see and sort of what we've shown is that like if M is growing faster than square root R, then you will get something that sends the average waiting time to 0 like significantly faster than the M is less than square root R case, right? But here, I mean, yeah, I can't say that there's like actually some kind of phase transition that happens besides the square root R point.
So just a quick question there on that.
Mhm.
So you're motivating the fact that you shouldn't have too many idle servers by an energy cost. So in a real system, would this scaling of 0.75 be a something that they would implement, or would it be too much? I mean, just as a comparison point. I mean, I know these are, you can set different functions and get different trade-offs, but what happens in practice would be.
Right. That's a good question. I feel like, I mean, even for these values of k, I think probably what people would end up doing is just choosing like some like constant fraction of the number of servers instead of like scaling it in this particular way. Because even the scaling here is sort of wonky if you're only dealing with like 100 to 1,000 servers, right? Like the rounding errors end up making like a pretty significant difference, like 1 or 2 servers like matters. And so likely I would anticipate they just use a constant fraction. But some of the other strategies that people use are things like using some kind of like delayed off mechanism or doing some sort of like if you're doing dynamic provisioning, oftentimes you'll be sort of estimating the arrival rate within some window and using that to like, you know, make predictions. And there are sort of machine learning approaches to being able to predict load. Like if something goes viral, you want to like anticipate that and start things up ahead of time. And we're really like from a theoretical point of view, we're like not really close to being able to analyze what people do in practice. But I think in a lot of cases, like if they're doing something simple, they're doing something probably close to this. And in that case, they're probably not thinking about any kind of funny scaling. They're probably just doing constant fraction.
Thank you.
Yeah, thanks for the question. Okay. So this is sort of a visual representation of our results in the scaling M case. Right. And so as we discussed before, showed that M has to grow faster than the square root of R in order to like have some kind of significant effect on the average waiting time. Okay. Right. And of course, that line I showed you before wasn't just a random line. I was actually just plotting the approximation that we got. And so now that you have this approximation, if you're going to use it for provisioning, you're going to do a much better job than you would have been able to previously. Okay. All right. And so now that we've covered the sort of theoretical results, I want to talk, I guess, extremely briefly about the sort of the techniques that allowed us to derive these kind of, in my opinion, pretty cool results. And so we'll start by describing the sort of initial approach that we took, and then I'll describe two sort of key technical challenges and two key ideas allowed us to get past them. Okay, and so the first thing that we did is just apply apply Little's law, so that instead of thinking about the expected response time or expected waiting time of a job, we can instead thinking about the expected number of jobs in our system in steady state. Okay. Okay. And the way we approached understanding the steady state number of jobs was to use the renewal reward theorem. Okay. And the basic gist of the renewal reward theorem is to realize that there are certain points in our state space where the system evolution between consecutive points is independently and identically distributed, right? And these points are called renewal points. And what the renewal reward theorem tells you is that if you want to look at the steady state expectation of some function of your state, for example, the number of jobs, then it's sufficient to look at the area under these curves, the expected area under these curves, divided by the expected length. And that comes about because of like kind of a strong law of large numbers kind of effect that happens when you add these IID things together. Okay. So that's the basic approach. Okay, and the real benefit of doing this is that now you can express the time average of the number of jobs in terms of time integrals, like sample path integrals over a renewal cycle. Okay. And so the first challenge actually is in choosing our renewal cycle, right? It's not obvious how we should define a renewal point so that we can go through this chopping up process in the first place. Okay. And the key idea here is to look at the MM1 setup. Okay. And if you've taken queuing theory 101, then you'll sort of maybe recognize this picture. This is describing the typical renewal cycle that one uses to analyze the MM1 setup. So you start the system with the queue empty. At some point, a job arrives. Okay. While the server is setting up, jobs continue arriving, right? And you get some kind of linear increase in the number of jobs in your system. At some point, once the setup time has elapsed, the job turns on and you sort of start a busy period where the server is continuously working until the system eventually empties, right? And then you're back at square one. Okay, and this description, like if you sort of go through all the mapping, this kind of description is enough to get you the average queue length and the MM1 setup, just from this description. Okay. All right, so you have your arrival, turns on, it turns off. Okay. And so there are two ways you might think about generalizing this to the multi-server setting. The first way is that you're moving from having jobs in your system to having no jobs in your system, right? Okay. And in that case, you end up going from like one server to 0 servers. Okay. Another way of thinking about this, though, is to think about moving from stability to instability. Right? And that's when you turn off your server, somehow you don't have enough service capacity to be able to handle the jobs that are arriving to your system time, right? Your service capacity is 0 while jobs are arriving at rate lambda. Okay? And likewise, when your server finally turns on, you now have like in excess of, you have an abundance of service capacity, right? Because you're able to stabilize your system, obviously. Right? And so this transition point from stability to instability is precisely how we define a renewal cycle. Now, of course, if you try to use this jobs to no jobs transition in the multi-server setting, that doesn't end up working. But if you define your renewal around stability, this transition from R+1 servers to R servers, then you're going to get like a pretty nice renewal cycle. And actually, if you look at traces, like it seems like there is a right renewal cycle to pick, and this is it.
Sorry, it's R again.
R is K times rho, and it's the average number of busy servers in your system. Alternatively, you can think about R as the number of servers that is required to stabilize your arrival rate. It's sort of naturally, because of that sort of natural why you consider R+1 R. Okay. So that's one technical challenge, and this ends up actually having another benefit. It sort of it allows us to nicely decompose a renewal cycle into two different parts, right? When the R+1 server turns off, now we've entered an instability phase, and in general, our queue will sort of start to accumulate. Right? And then at some point, this R+1 server will turn back on and we'll enter a draining period, because we're never going to turn off a server while we still have jobs in the system, jobs waiting in the queue, right? And so we're going to enter a draining period of our queue until eventually that R+1 server turns off again and we start over again. Okay. And this decomposition actually turns out to be like immensely useful in actually analyzing the system, because now you have an upper bound on the number of servers that are active during the first part of this renewal cycle, and you have a lower bound on the number of servers that are active during the second part of this renewal cycle. Okay. Now, the second challenge that I'm not going to have a ton of time to present is the actually analyzing these time intervals you get after you do this decomposition. And the technique that we developed to do this is called MIST. And I think I'm just going to describe sort of the simple example, which has to do with an MM1 busy period, and sort of illustrates what's going on in MIST. Okay, so we're going to consider an MM1 queue starting empty at time equal to 0. And then we're going to define some stopping time t long to be the first time a busy period lasts longer than some parameter gamma. Okay, and that's fixed. Okay, so imagine your system, your server breaks if it runs for longer than gamma time continues. Okay, assuming you know the distribution of the length of a busy period, what's the expected value of t long? Okay, and what you can do is you can make a geometric argument. You start with the system empty. At some point, a job arrives, okay? And if the busy period is longer than gamma, then t long occurs and you're done. But if it's smaller than gamma, then your system is empty again and you've basically started over, okay? And so you can argue that the number of busy periods you make is geometric, where the probability of success is just the probability that a busy period is longer than gamma. And this will actually exactly allow you to get the expected value of t long. Okay. Now, I don't have time to exactly explain how you end up using that, but one example is that you end up using that to bound the length of this accumulation phase. And there's a pretty like nice relationship between these two things. But I'm going to skip through it because I don't think we have the time. But it's interesting stuff, and you can talk to me offline if you're interested in it, or you can send me an email, whatever. I'm happy to talk about this stuff. I think it's pretty cool. Okay, so we skip through. What I want to do is give you a high-level impression of what the method of intervening stopping times is, this MIST method. And the basic gist of this is that if you're trying to look at some function of time, f of t, and you have some initial stopping time and some final stopping time, then what you're going to do is define a sequence of regular intervening stopping times, sort of checkpoints in time, where you can make sure you know something about the system state that's relevant to your analysis. Okay, so you define these intervening stopping times, possibly a random number of them, and then once you've chopped up time and you've sort of constrained your state space to lie in some kind of nice region, you use coupling or busy period analysis or martingales or anything you want in order to figure out like the expected length of one of these slices. Okay, so at times we even use MIST again to sort of recursively try to analyze one of these slices. And you can think of this as sort of like this allows you to make sort of a sequence of coupling arguments, where, you know, like if you think about like normal state space methods, like usually you're just trying to show that usually you're making some kind of argument about the sort of drift in steady state, depending on where you are in state space. Whereas here, we allow you to explicitly consider a sequence of a specific sequence of coupling arguments. And in doing this, you're like able to make worst case bounds that are like somewhat nicer than you would be able to do than if you use sort of existing methods. And I would love to explain more, but I don't think I have the time to. And so just as far as future work goes, just to kind of give you an idea of what I'm interested in right now. In the future, I'd be interested in doing like more of this setup work. In particular, I'm interested in like how setup ends up occurring in practice. I'd be interested to look at sort of industry traces or cases in sort of computing. So what's the right way to say this? I'd like to sort of be able to have like a direct impact in sort of the guidance of the development of these systems. And so, yeah, I'm really interested in applications to the setup time work. Another thing I'm interested in is scheduling with deadlines. So assume that like after a job arrives, like you have 10 seconds or something before it expires. We have sort of some policies for scheduling those jobs, but we don't have like a great idea of like how far we are from optimality with respect to those policies. And so I've been looking into that recently. Another thing that I've sort of been interested in, sort of been thinking about how to approach is queuing in the appointment setting. So a lot of times, I mean, everyone's been to a doctor's appointment where there's an appointment sort of starts at 10, you get there at like maybe 9:55, and then maybe you end up waiting 30 minutes to an hour because things are running behind, right? And I'd love to be able to like sort of model the queuing delays that end up arising in a healthcare setting or really with any kind of appointment setting, and to think about, you know, what ways we can change how we're interacting with like what's the right way to say this? How we can sort of modify the way that we're taking appointments and providing service so that we can mitigate these queuing delays, if that's at all possible. And another thing that I've been interested in recently is reinforcement learning, in particular hierarchical and goal condition reinforcement learning. I've been looking at it from like a theoretical point of view, and yeah, I'm just sort of interested in what we can do to sort of enhance generalization. So yeah, that's what I have, and I think we're well. I've heard you're supposed to finish a talk by giving a joke, but I couldn't really think of a setup, so well, I'll just open the floor for questions.
So Jalani, maybe so you presented a lot on deterministic setup times, and which you said was close to. Can the method be extended to other kinds of setup times? If it's a base type or something else, I mean.
Right. So this is a good question. Whether this method can be like extended to phase type or something further. I do think it's possible. I think it's possible to use this method to analyze the exponential setup system. And I think if you can do that, it's just a matter of grinding things out to get to the phase type system. It's not clear to me, like in the phase type case, exactly how the work would scale, like how much writing, for example, it would take in order to get like some kind of appreciable phase type result, whether it need to be like broken up into multiple papers or something. But I
was thinking even if you can go from,
yeah,
say, exponential to deterministic through Erlang, right? So sequences are
right.
if somehow getting there to show that, I mean, how do you trade off from exponential to deterministic? I mean, that might be reasonable.
Right. This is a good question. So one thing about, I guess, one thing about the method that I'm using is that it's sort of tailored to work in the case where setup times are deterministic, or I say tailored in that it sort of works most cleanly when setup times are deterministic. If you don't use, if setup times aren't deterministic, then you end up needing to use like sort of probability bounds, where like you use sort of concentration around the mean in order to make some kind of extended argument. And so, what's my point here? My point here is that, yeah, I guess I think it could work. It's not clear to me how you end up going from like deterministic to exponential through Erlang. Like it's clear to me how you would scale that the other way, right? It's clear to me like that they're equivalent, like in the limit, but it's also not super clear to me like how you would work back in terms of the argument in the opposite direction.
Yeah, I mean, I'm just curious in some sense, right? I mean,
Yeah, but it does feel like you should be able to do it. And I have thought a little bit about it. I've thought more than a little bit. I've thought a decent bit about it. And I'd be down to talk more about it if you're interested.
When you showed your nice examples, but again, the server spinning up. I mean, I can certainly think of examples where I just jump ship when the queue is too long.
Right.
So I don't know if that's the same as deadline. I'm not sure if I was waiting based on a given amount of time. Or if it's like the number of people ahead of me in the queue, but is there analysis under maybe the non-setup time setting, or is there any progress on this situation?
Yeah, so there's progress. So traditionally that model is called abandonment. And in the non-setup setting, yeah, people have studied that a lot. So there's a lot of results about, someone is impatient and they decide to, right? The interesting thing about that line of work, at least to me, is that in settings where there is this impatience or there is this abandonment, you end up with sort of like there's like a regularizing effect on the queue length, right? Because if the queue length is too long, you're like, I'm not going to go into it. And so this sort of prevents the queue length from getting too long. And so you might imagine like in the sort of cartoon example that I showed of a renewal cycle, like if abandonment was in the system, then maybe you wouldn't get this gigantic peak. We'd get sort of some kind of rounded off peak because at some point people would be like, oh, it's not working, and leave. Yeah.
And I guess expected waiting time is not the most relevant metric if you're trying to sell services.
Right. Yeah, so in a lot of cases, people sort of define quality of service not just by the average waiting time, it's by like some kind of tail condition where, yeah, you need to be served within.
Rate.
So actually that reminds me, there's another question I had. And so you're able to get the, using Little's law, so you're basically looking at the mean number of customers in the system.
Mm-hmm.
Can you say anything more about the distribution, even say the tail of it, or?
Right.
So this is not waiting time, just the number of customers. I mean, I just want to know how that system behaves in some way.
Yeah, I think you could. I think if you defined your stopping times in the appropriate way and you sort of interlace those stopping times with the existing stopping times that I'm already using in my analysis, I think you could probably make a decently strong statement about the tail behavior of the system in terms of the number of jobs. Of course, you need to convert between like the no, I guess it's sort of automatically handled by the there. Never mind. Yeah, I think you could definitely do it.
Yeah, weird. I'm slightly off. Just so you did a lot of simulations. I'm curious what your preferred tool is for doing the simulation.
Right, right. So my initial tool for attempting to do the simulations was Python. Just because it's easy to write things in Python. It was way too slow. And so I switched over to C++.
Okay,
Yeah.
thanks. I've done both, so
Yeah. And even that, even in C++, it ends up taking a pretty long time just because there's like a lot of variance in the simulations. So, yeah. Any other questions?
That's like,
So maybe just one last question was, so these are not Markovian systems, right? So how do you, I mean, so how do you define stationarity, or, I mean, how do you know you're, I mean, in simulations, I can see that, but is there a way to say, hey, you're close to stationarity? Because the Markovian, I mean, you'll have to put in a lot of information to make it a Markovian system and then check mixing times and various things, right? So
Yeah. So I guess it's, yeah. Yeah, it's Markovian with like a continuous state space, right?
yeah, but then you understanding how fast it's, how close it's to stationarity is a little harder, right? I mean,
That's true if we were thinking about like some kind of Markov chain mixing, but like even in that case, like if you think about what the state variables are, like remaining setup times, there's basically like if you have two remaining setup times in your state, like probability 0 that you ever like get back into that state again. And so yeah, I guess
but I think maybe since you're using, you have renewal times, then it's probably okay. If you count the number of renewal events, you can sort of get a better sense of, you get some accuracy of, you can give some accuracy confidence estimates for your, for your, I mean, for what you're estimating, right? So I think maybe that's how you want to handle the simulation being accurate or not. Yeah.
yeah. And so I think the simulations I think are accurate. I ended up actually doing this. And it sort of comes from the theoretical results somewhat in that like I know the expected length of a renewal cycle. And so I can just keep track of the number of renewal cycles. And that's sort of sufficient for me to get like a pretty good estimate of what's going on. But yeah, it ends up being the case that renewal cycles are somewhat long in terms of the number of events, I guess. Like if like 500 jobs are arriving per second and your setup time is like 1,000 seconds or something, you end up with like a huge number of arrivals happening just in the context of like a single renewal cycle. But yeah, this is a good point.
And in that context, maybe if you, I mean, if you take if you approximate your deterministic setup times with an Erlang, maybe things will run faster because it still has a Markovian representation. It's simpler.
Yeah, that's a good point. That's a
But
good point.
usually up to 10, at 10 Erlang, you're as good as deterministic, more or less, statistically, for most problems. Right? Yeah.
Yeah, I've actually I don't know if I have it in this presentation, but I was talking to Jamal. I guess I don't have it in this presentation, but I ended up simulating like for various values of Erlang just to see how that scaling ends up working out. And you're basically right that I could just be using like a 10 stage Erlang or something. Yeah, that's a good point.
I have no more questions. I know we ran way out of time, so I'll let you finish.
Yeah, I mean, I'd be happy to talk sometime offline, whenever it's convenient for you if you're interested.
Sure.
Yeah. Yeah. Okay. In that case, I'm gonna sign off.
Thank you.
Thank you.